All right. Thank you, Jan, for the introduction. Thank you, Gerhard, wherever you are, for inviting me again, with probably almost the same title. And I'll have to disappoint you right away. No weak values in this talk. But I'm very thankful to many of the things that Ephraim said this morning, because they actually do play a role here. All right, let me start by introducing the group before I forget. So this is the whole group, and the people who are involved are in here. There's a postdoc, Robert Keil, and a PhD student, Thomas Couten. Now this guy has left and actually been replaced by another one who's not yet on the picture. And I would also like to mention that I have two very important collaborators on this project. One sits right here, Czeslaw, who you all know, and another one who's in Jena and writes fantastic waveguides into glass just with a laser. And this is mostly funded so far by the Canadian Institute for Advanced Research, but we are happy to hear that we're probably going to get the grant to just pursue this, which has been difficult actually to obtain. All right, just a very quick recap. You all know about interference, and I don't want to go through any of the algebra here, but I just want to say that for the purpose of this talk, I'm going to define interference as sort of the difference between what you see for, say, 2 slits minus what you see for each slit on a particular point on the screen or at the output of an interferometer, whatever your system is. And the important thing is going to be that we're going to look at 3 paths or more to see how we could possibly go beyond quantum mechanics. And this is all goes back to Raphael Sorkin, who you'll see in a second. So if we multiply this out for 3 slits, then just by virtue of the fact that our probability is a square, according to Born's rule, we actually find that we can describe any interference phenomenon by just having all these sort of binary terms. So 3 interference terms in here. And if I regroup this a little bit and use the definition that I did on the previous page, I can actually show you that what you see somewhere on the screen behind the slits at a particular point when all the slits are open is really the sum of all the 2-slit combinations minus the single slits. And now, of course, there's been a lot of criticism, and maybe it'll come again, that really it's a little tricky in practice to say what are orthogonal wave functions, because of course I cannot split this in an arbitrary way. I have to refer to orthogonal subwave functions, psi A, psi B, psi C, and in practice, of course, they can only be approximately orthogonal, never perfectly. And so Raphael Sorkin thought about, and it turns out this is becoming more popular now after a while, thought about how we could break up quantum mechanics. Even if Gerhard is trying to reconstruct it from below, I'm going to try to break it up, and said, well, you know, has anyone ever measured this thing here? Measured sort of the left side minus the right, and it turned out no one has ever explicitly measured it. It's probably implicitly measured in many other situations. It's just really hard to dig out this little difference unless you do a dedicated null experiment. And so we expect that this thing would be 0, and so we would just try to measure all these terms by blocking the slits. And now, of course, it's also been said that blocking a slit is not the same as the slit not being there. And as an experimenter, you have to work hard to make it as similar as possible. And then we do some normalization, and we sort of normalize this 2nd-order interference, or sort of true 3-path interference by the regular 1st-order interference. And you know that we did an experiment a long time ago, and which had some deficiencies, but it happened to be the first one. And then I want to point out a few things that have come up since. On the theory side. In fact, some of these are earlier than the experiment. It turns out, of course, that if we break up quantum mechanics somewhere, probably the whole building would tumble down. It's not so easy to just take a little screw somewhere and tune it. Turns out you could build a super quantum computer that post-select itself and solve some problems that you couldn't solve with a quantum computer, or you could solve it much faster even than on a quantum computer. But there's also, in the structure of the theory, people have said that interesting things appear. For example, in Joe Emerson's group in Waterloo, they found that the absence of higher order interference is really equivalent to saying that we can reconstruct the state of a system by the regular tomography that only uses sort of binary interference in all the states. In fact, we actually encountered this in the experiment, an interesting conundrum between what we need to do for tomography and what we need to simulate the system. Then there is an interesting theory by Časlav on density cubes. He's probably not going to talk about it today or tomorrow. Sorry, and I won't say too much because only to say that instead of a matrix, he uses a cube. Okay, and then you have sort of space diagonal coherences, which obviously represent third order or second order interference, higher order interference. And just last week, actually 2 weeks ago, appeared 2 papers from Lee and Selby that somewhat criticized Časlav's theory, and I can't say I understand what they say. I haven't had the time to really read through this thoroughly, but they propose another type of theory that exhibits all higher orders of interference. And then there's some interesting connections between various bounds, but I don't have time really for that. So just also saying something about slits. Our original slit experiment had some difficulties, just very, very basic stuff. Hans de Reet pointed out that, well, closing a slit does not necessarily leave everything unchanged. And then there's another, I guess it's actually a connection between these two, a paper by my former collaborator, Ubushi, and her husband, who pointed out that if we sum up all the sort of non-classical terms in a Feynman style, we also get an effect, which is kind of saying that the wave functions are not orthogonal. And I'm sure Gerhard would know more about this. Okay, and there were some non-optical experiments that I should point. Oh, sorry, that's not true. There's one optical experiment that used spatial light modulators, and there was one non-optical experiment in NMR, and they all came out with sort of some bounds on this kappa. All right, so this was the scene, and now let me introduce you to our experimental setup, which looks maybe a little more complicated than it should be. So here's the interferometer. Here's the thing that we measure trying to measure higher order interference terms with. And you'll notice right away that there's 5 paths and not 3. So you'll ask why 5? I have several answers. The true and honest answer is that we had a beam split that made 5 beams. It turns out, though, that it's very useful to have more than just the 3, and you'll see in a second why. I should also say that we do these experiments in 3 different configurations. One of them I call for now classical, and this is really just a name. This doesn't actually mean anything. Where we simply use a red laser, this one here, and a regular photodiode. So in that sense, it's completely classical. Photons never appear in this type of experiment, not at the source stage and not at the detector stage. And in between, you can choose your representation. Then we have another one where we still keep the red laser, but use a single photon detector. So at the end of the experiment, we have clicks. And then we have a third configuration where now we use a heralded single photon source, as we've seen it already a few times in this conference. A blue laser excites a crystal, and that crystal makes pairs of photons. We detect one and use the other one as a conditional single photon. So it's been heralded by its partner photon. And in that case, I would say that at the source stage, we can be sort of sure that there's one photon, and then obviously in that case, the detector also has to be a photon counter. So I call these the classical, semi-classical, and quantum regimes, and we can debate whether that's a good designation or not. Now, just a quick photo. Actually, this looks quite crowded because now we have 5 beams and we have 4 non-trivial phases. In fact, we need to do all 5 because it's really hard to adjust 4 phases if the one is wrong. Okay, so these are little phase shifters, and then we have an array of shutters. I don't know if you can see this here. So there's 5 holes here that can actually close the beams. And this is nice about the interferometer. It's so large that you can actually stick your finger in and you can really block the beam. And so if you wonder, how long is, or what's the probability for the one photon to do a loop around the other slit, it's really long. It's many, many, many thousand wavelengths. And so it's going to be very unlikely, I would say. All right. And so now we do this. And as I said, we're going to measure this. We're just going to measure all these combinations. And so a first result might look like this after we collect for a while, in this case with a single photon detector and probably with a laser. We measure this quantity kappa with an index 3, meaning that it's now, this is really for 3-path interferometers, it's the higher order interference term over the regular interference term. And as you see right away, the center of this distribution marked here by the black line is really not at 0. It's somewhere else. So you would say, here they've actually found that quantum mechanics is wrong. There must be higher order interference. But any good experimentalist would know that before you publish something like this, you go and look for your mistakes. And to do this thoroughly, we actually went through correlation analysis. And here is one of the advantages of this 5-path interferometer. A 5-path interferometer actually has 10 3-path interferometers contained. But they're not all independent, so we have to be a little careful. They don't produce independent errors necessarily. So here's a correlation matrix, and also here's some autocorrelation of subsequent measurements. There's actually a 1 here, but it seems that really we are in this regime where we have no correlated noise. As Ephraim pointed out, we do this in random order and wait long enough for anything to subside. So when we do this error analysis properly with all the correlated errors that appear, we find the following. So for these 3 different regimes, you can see the powers of 10 are, if we use a laser at high power and not very high power and the photodiode, we can get a lot of data, with very low fluctuations. So that's why here we are on a scale of 10 to the minus 5, whereas if we do it in the semi-classical regime with photon counting, we're at 10 to the minus 4, and if we do it with the heralded single photons, we're at 10 to the minus 3. And now you would say, well, couldn't you make up your mind somehow? Here's plus 9, this is minus 9. Of course, this is a bit larger than that, but clearly something's wrong here. And for those of you who've heard me speak about this before, you already know the answer. What's important, of course, is that the standard deviations here are all smaller than these values, right? So we would be excluding the 0, but we don't even know which way. And this is kind of difficult. And so, as you know, we've been occupied quite a bit with checking the nonlinearity of our detectors. And in fact, every detector you buy and use will respond nonlinearly at some point. Ephraim pointed out this morning that a detector would saturate, right? A photon counter, eventually, it has a dead time, and at some point, maybe it counts 20 megahertz of photons, and that's it. So that's maximally nonlinear at that point. And so we measure this nonlinearity by simply doing a non-interferometric measurement. So we measure both two different beams, independent sources, one of them, the other one, and nothing. And from that, you can essentially then try to fit a model, a nonlinearity model. And this measurement does not use interference. It just uses sort of the addition of energy or power onto one detector without interference. And it turns out, you would think that these detectors are maybe well calibrated, and if you buy a detector for 10,000 euros, they would tell you what it is, and they might give you something, but the specification they give you is so coarse that we would not be on the scale here of my table before, because they might power meter, very expensive power meter might tell you 0.5% nonlinearity maximal, but if it was that badly nonlinear, we would not be measuring anything here. It would be really bad. Okay, so we worked really hard on getting a very low nonlinearity photodiode-based detector, which now is actually at a level of 8 ppm. This is a bit of an older measurement. So here's the residual signal over the total signal, and I'll look at the time. I have to finish up soon. So let me just skip over this. Here's the photon counter. As expected, it saturates simply because it's dead for a little while after it has measured a photon. So this is kind of easy to model. And then in order to create a prediction for what we expect to see from quantum mechanics, we also need to characterize the interferometer itself and know what kind of intermediate state we have, so that we can then add the nonlinearity onto this density matrix and generate predictions for the output of the interferometer. And this is the sort of the density matrix of a roughly equal superposition of these 5 beam paths. All right, and this is the predictions we generate with different types of reconstructions, which actually don't matter so much. So here's single, double, triple, quadruple, and the 5-path term. And once we add this all in, we can generate what we expect quantum mechanics plus the nonlinearity to generate in terms of a apparent higher order interference. And once we do that, we see that the measurements are actually not that far off. So on the right side is what we measure with the laser in the classical and semi-classical regimes. And then there's always a sort of the theory points next to it. And you see that the theory sort of, and with the error bar of the theory, kind of nicely overlaps with the experimental data. And the same is true for these semi-classical measurements, except that they are totally a little farther off, because the nonlinearity of the photon count is actually worse than the nonlinearity of the linear photodiode. It's much worse in a way. I mean, you saw that on the curve, and that's why it actually deviates much more in the raw data. And then the surprising thing is, for a long while, I was under the impression that if I had a heralded single photon source, really I didn't have to bother with nonlinearity, but it's not true again. I'm actually bothered by the nonlinearity, both of the detector on the interferometer and on the heralding detector. It just gets convoluted into a much more complicated formula. And one of the things we really want to do is improve that heralded single photon source to make it sort of a pulsed heralded single photon source where we can avoid dead time effects. All right, and this is then when we subtract. So this is delta kappa, the expected nonlinearity minus the data, or vice versa. And you see that now I can sleep well again. It seems that quantum mechanics is sort of at least allowable under these conditions, and we can all go home and study it some more. All right, and just for the last minute, let me show that this has some developments. I'm not going to talk about the quaternions as I had in my abstract, because it doesn't fit into the time. But there we had to make interferometers that are much higher visibility, so of much higher quality. So we went to waveguides. We built, this is what Alex Samite does. He writes waveguides into this glass chip with a femtosecond laser, and this is a picture of the chip. However, we tried to do it with this kind of just a simple beam splitter, and then to reflect the beams back, and it works. Sort of, we put a mirror right here and really reflect the beam back into the waveguide, but it's also a real pain, and it's extremely slow. Apparently, this thing keeps oscillating after we move the mirror for a long time. So it works, but it's also not the way to go. And right now they're working. It turns out they can actually write little holes into the glass too with the laser. I mean, they write and then they etch, and now they're backfilling these holes with liquid crystals, and so hopefully we'll have an interferometer where we can actually control the phase with the liquid crystal modulator, and also control the throughput, so the attenuation, with a little Mach Zehnder as a modulator. All right, and that's it. Let me just sum up, and if you want to tell your people at home what are the values, that's the values depending on your choice of measurement system. I can give you 10 to the minus 5, 10 to the minus 4, or 10 to the minus 3, roughly with a 1, 2, or 3 coefficient in front. And if you have any ideas how to do this even better, maybe in an atomic system where we can get much better statistics, be my guest. I don't know if there's any weak value way of amplifying and thus improving the statistics. I would love to hear it. Thank you.
Thank you.